All right, so we're going to continue talking about Poroelasticity, and was the last thing that we saw, that how to obtain an equation of energy of a system based on strains, and now since we have a porous solid, adding pore pressure. And this was the final equation that we found. And remember that we just did the analogy of strain energy of an elastic solid. If you take the area, this is the energy, and this is the equation. And similar to that, you can do the same for shear and for adding the terms of pore pressure and strain. I'd like that you notice one more thing is that according to this equation that we have right now, and according to this one, what would be if I were to take a partial derivative of the energy with respect to the volumetric strain using this function? One more thing, there was a small mistake here. This is not a differential, this is a total. So now that we have this function of work, if I take the derivative of that function with respect to volumetric strain, that would be equal to what? You guys remember about derivatives? Yes, so these 2 goes down here, and 2 divided by 2 is just 1. It's just going to be K times the volumetric strain. And notice from this equation too that that partial derivative is actually the mean stress. And we're going to do the same thing, but now apply to this long equation. So we not only get the mean stress, but also we get the shear stresses, and also we get the variation of the energy of the solid with pore pressure. And once we do that, we'll get all the equations that we need in order to explain the deformation behavior of this porous solid. Okay, but that's what we're doing. We're taking derivatives with respect to this one and with respect to porosity later, and that's going to give us a function that's going to allow me to mix mean total stress with pore pressure and also porosity and volumetric strain. All right, so let's see if this works, so I don't have to write this equation again. Okay, so then let's start with the first one. We'll take the derivative of that energy function with respect to the mean total, the volumetric strain, and similarly to the previous case that we did over here, we have volumetric strain over there, so this is going to be K times volumetric strain. So second term, do we have anything there? No, we don't have any variable which is volumetric strain, so the derivative is 0. Here we do have 1, and the derivative of this function is going to be negative alpha, because this is the variable. The derivative of that is 1, and the next one we don't have anything. So it stays like that. Let's go with the second term. We're going to do derivatives with respect to the shear strains. Yes. Zoom out a little bit. Okay. The second one, there is shear strain here. There is no shear strain here or there. The only term here is going to be the strain the shear strain squared, when I take derivative, it's going to be 2 times shear modulus times the shear strain. And that's it. And for the last one, we're going to have a variation of free energy with respect to pressure. And there is nothing in the first term, nothing in the second, but then we start to see pressure in the third and the fourth. And this is going to be negative alpha volumetric strain. And these 2 is going to come over here. It's going to simplify with the 2. And therefore, we are just going to be divided by n. And wait, there is something here which I am forgetting. Okay, I think it's okay. It's a negative sign, right? Yeah, that's negative. And that should be okay. Okay, I remember what it is. Just for convenience and for the change of variables that we need for this third equation, instead of just a plain partial derivative, we have to take the negative of the partial derivative. And so these 2 are going to be positive. All right, so similarly to what we did in this equation, and recognizing each of these terms over here, we can do the same with the 3 new equations that we wrote. And the first one is going to be the total mean stress. Second one is going to be the shear stress. And the third one, and that's why it has a negative term, is going to be the change of porosity phi. And these are the 3 equations of Poroelasticity. Notice that the first one, let's put numbers, it's sort of an effective stress equation, because it tells you what is total stress as a function of this quantity here, which is going to be equivalent to an effective stress, and a pore pressure corrected by a coefficient alpha. The second equation is the same as in any solid. It's just shear stress is equal to shear modulus times shear strain. And that kind of makes sense, because fluids cannot apply shear on solids, and therefore it is the same. Having pores or not, or having a different pore pressure or not, is going to be the same. And the third equation, it relates changes of porosity with changes of pore pressure of the fluid and volumetric strains. And this is something that we didn't have before. Now we have an equation which is corrected by this new coefficient, but before we didn't have anything like this that will tell us changes of porosity with changes of volumetric strain and changes of pore pressure. So this is fairly new. All right, so if you take a look at these equations, you will see that there are some variables here which are properties of the medium. For example, this one is a bulk modulus, is a property of the medium. Let me do it with another color. G is a shear modulus, is a property of the medium too. And let me see if there is another one that we don't know. No, I think that's fine. We already knew what was K, what was G. But look at the new variables. We have alpha. And alpha is again here. And this is the pressure, this is a P. and we have N. Those are properties of the materials, and that's what we would like to know now. What are alpha and what are N? I'm going to give you an advance about this, a preview. The alpha is the so-called Biot coefficient. So Biot was the person who developed this theory originally, and that's why it is called the Biot Poroelastic coefficient. And N is something which is called a Poroelastic modulus, a lot less popular than the Biot coefficient, but it's super important too. Okay, so let's see how now we determine what alpha and N are. And in order to do that, we're going to do an experiment here in class in which we'll subject a porous solid to a very specific condition, something which is called unjacketed loading. So it's called unjacketed because it doesn't have a jacket. You may wonder what I mean with that. Here we have a small triaxial cell. Did I show this to you guys or not? Okay, well, I can do it again. So this is the triaxial cell. So inside is hollow, and then you put the rock inside here. There is a lid that goes here on the top, but most importantly, this is what goes inside. Here we have usually we have an end cap, bottom end cap, top end cap, which will be, this will be the bottom end cap. This one will be the top end cap. And in the middle, we put the rock, which I don't have it in this case. And then all of this goes inside this membrane. So the final assembly looks something like this. Probably you're going to see very well in the video, but I want to show you anyways for those that will look the video. But it looks something like this, right? So bottom end cap, top end cap, membrane, and inside you have the rock. And this membrane or jacket is what separates the confining fluid from the pore fluid inside. So you can apply a pressure outside or a confining pressure which is different than the pore pressure. Okay, so then again the rock goes in here, and the jacket goes around and separates the two fluids. Okay, we'll do this experiment later on, but not right now for this one, because this one is an unjacketed loading. And that's going to mean that we're not going to use any jacket at all. And in this type of experiment, we're just going to get a porous solid. Can be anything. Something nice about theory of Poroelasticity is that you can use it for rocks, but also you can use it to explain the formation of bone. You can use it to explain the formation of organic tissue, or even other things than bones. For example, I had a PhD, a friend, when I was doing my PhD, that he did simulations of the formation of brain when you open the skull, if you have something, if you need to do a surgery. And how that swells depends on the porosity of the tissue, the brain tissue, and it can be also used with this theory. All right. To this porous solid, we're going to apply a pore pressure and a confining pressure which are going to be the same. So basically, this is just an experiment in which you submerge a solid into a fluid, let's say water, and you just increase the pressure of the fluid. So for example, for this particular fluid, we could immerse it inside this vessel, close it, and just increase the pressure. For this particular case, we are going to assume also that all the porosity is connected. So when we increase the pressure outside, the fluid gets also inside the pores and applies a pressure inside the pores which is equal to the pressure outside. So that's going to be the same pressure. And let me write this down. Porosity is all connected. That's going to be very important to derive the equations that we want. And now let's use the equations that we just derived before. So for equation number 1, let's take a look at that equation. I have that bulk modulus times volumetric strain minus alpha times the pore pressure, that has to be equal to the total stress. The total stress in this particular problem is just the pressure outside. That's the stress I'm applying on the solid. And because it's a pressure and it has a positive value, it's going to apply a compression, and therefore the total stress is going to be negative P. That's going to be the total stress, mean stress SM. And notice that it's the same in all directions. So if now, since I know pressure, or I can control pressure, I'm going to calculate what is the volumetric strain due to an increase of pressure, and basically I just have to move this one to the other side, right? And then if I take the common factor P, this is going to be -1 plus alpha divided by K, or since I know that alpha is going to be less than 1, let me change that to negative P 1 minus alpha divided by K. So what this equation tells you is that you have a positive pressure, then your solid, your porous solid should shrink. It should be negative because we have this negative sign over here. So even if, I mean, if you didn't have a porous solid, you apply pressure from all sides, the solid should shrink. If you do have a porous solid, similar to the foam cap that I showed you last time, and if you have connected porosity, the solid is also going to shrink. And let's see why is that. So, but you know, if it doesn't have pores, we all agree that it's going to shrink, right? If it does have pores, it is also going to shrink, because let me find a good candidate pore over here to do this. Let me choose this, but I'll move it a little bit. Let's say that I have a pore somewhere over here. If I were to select a piece of solid somewhere in there, let's say that on the bottom it feels the pressure from the fluid from outside, but on the top it also feels the pressure from inside, because the pressure we say in the pores is the same as outside the rock. And on the sides also we have a pressure that needs to go through this side and it needs to be balanced to the other side going through the solid. So in this direction, we also are going to have a stress in the solid matrix, which is going to be P. So at the end of the day, the pressure or the stress in any part of the solid is going to be equal to the pressure. And because of that, the strain of the solid part is going to be proportional to the pressure and inversely proportional to, what do you think? This K, remember, it's a bulk quantity. It's the K of the entire porous solid. So if I talk about the strain of the solid part, then which K should we use? Of the solid. And that's going to be Ks, or the K of the solid part. All right. So now that I have those two, I think that it is clear where I got this equation, right? I just say that the state of stress everywhere in the solid is going to be equal to a compression. In all directions, it's going to be P, and therefore this is going to be the strain of the solid. Okay, this is a little bit more difficult to see, but believe me that it's also valid. If this part of the solid is compressing in an amount epsilon s, and any other part of the solid is also compressing in an amount epsilon s, that means that the entire solid also is going to compress an amount epsilon s. The pores are going to get smaller, the solid is going to get smaller, everything is going to get smaller, and all of those are going to get smaller in amount epsilon s. And if that's the case, I can use these two equations, the ones with the two dots, epsilon equal to epsilon s, and this is going to be like this, divided by k, and this one is going to be negative P divided Ks. Notice that we have pressure on both sides, and we have a negative here. Let's make it a positive. And the last thing I'm going to do is I'm going to look for what we didn't know, which was alpha. Yes. And from this equation, if I solve for alpha, the result is going to be that alpha is going to be equal to 1 minus k over ks, where I'm assuming that all the porosity is connected. K, again, is the bulk modulus of the porous solid, and Ks is the bulk modulus of the solid matrix. At this point, you know, the use of bulk, it might be a little bit confusing sometimes, because sometimes we refer with bulk, meaning that putting everything together, and talking about, for example, bulk modulus in elasticity is about talking about volumetric strains. But here, we mean that, but also when we have a heterogeneous solid, talking about bulk, it means putting all the heterogeneities together. So in this case, with bulk, I'm referring to the part of volumetric strain. So K and Ks, the stiffness of the entire porous solid, and this is the stiffness of the solid matrix. So which one is bigger, K or Ks? Ks has to be bigger because K includes the pores, so it should be smaller. And if Ks is bigger than K, what does that mean for alpha? Alpha has to be equal or less than 1. And the Beot coefficient will always be equal or less than 1. Very porous solids, they have a Beot coefficient that approaches 1. Tight solids have a Beot coefficient that approach or that are less than 1. Some very tight solids may have a Beot coefficient which is 0.3, 0.4. Let me see if I find here a plot about that, because I had a good summary of those properties from a database I'm putting together. If not, I'll share it with you next time. And I think I have it in my other book. Okay, I'll try to remember to bring that page, but basically it's a compilation of typical Beot coefficient for rocks with as a function of porosity and a function of permeability. And basically what you see in there is that the higher the porosity of the rock, the bigger the Beot coefficient. The higher the permeability of the rock, the bigger the Beot coefficient. You go into tight rocks like shales with low porosity and low permeability, and the Beot coefficient goes down. Which makes sense because that means that the deformation goes into porosity, but also goes a lot into deforming the solid part. You had a question, Stephanie?
Is this in your book?
No, no, it's not in my book. It's not in my book. It's in some other notes I don't have with me right now. Okay, all right. So Beot coefficient then for this particular case, you can calculate it with this formula. But basically, what it's telling you is the relationship between the bulk modulus of the porous solid and the bulk modulus of the solid matrix. And as we said, the lower the porosity, the lower the Beot coefficient. Okay, so we are half done with this equation and with this test. Let's do, we're half done because we have alpha. Now we have to get n. And for n, we'll do something similar. Well, it's actually exactly the same test to get n, but we need to get the other equation. All right, so yes.
So the question, but how do you get the bulk, or yeah, the bulk modulus of just a solid with no pore space?
Just a solid.
Yes. Like
Okay.
How are you getting rid of all of the pore space when you're finding it out?
Okay, well, that's a good question. I'll tell you how you get the two of these. If you're just interested in the bulk modulus of the solid, usually what you do is you do tests on materials that don't have any pores, like for example, in a piece of crystal of quartz, on a crystal of calcite.
So you look at a single crystal level.
Yes, or sometimes you have like large crystals that you can use that in order to measure these KS. That would be the. And many times also you do with, instead of if you have an irregular shape, for example, you're not going to find a crystal with a cylindrical shape, right? So instead of that, what you do is you measure wave velocities, Vp and Vs, and with those two and the density of the material, you can get the K of the material using the theory of elasticity. The Ks of a given mineral, okay? We'll see later how to compute this Ks for a porous solid. But for if you have a rock which is 100% quartz, then your Ks, and with all connected porosity, your Ks is going to be the Ks of quartz. How do you measure K? It's you put a jacket around the rock, and then you apply a pressure around the rock, which is going to be called a confining pressure, which is going to be the same in all directions. And by increasing that, and measuring the deformation as you increase the pressure, you can measure the bulk modulus of the rock. And actually, that's going to be something which is called jacketed, because now it has a jacket. And also, it's going to be drained. We'll see why that later on. But it's going to have those two names. Let me improve the resolution of this. Okay. Okay, but those are very good questions, and we're going to get a little bit more in detail about that just right after we find what this parameter n is. Okay, so I use the first equation to get alpha for this unjacketed loading experiment. Now I'm going to use the third equation in order to get n. And that third equation is alpha times that plus p divided by n, and that's going to be porosity. So from the previous experiment, we saw that the volumetric strain of the entire solid, when we do this unjacketed loading, is going to be bulk modulus of the solid. This is still going to be the same. This is the change of porosity. And you remember that I was telling you that if we divide change of porosity divided initial porosity, we get a porosity strain. And I was telling you right before that using this logic that every single part of the solid here is subjected to a compressional state of stress with P in all directions. If this is the case, and if everything gets smaller the same amount, that means that the pores, they have to get smaller also the same amount. So if I have a volumetric strain, the solid part, let's say of 1%, our porosity is also going to change 1%. So that porosity strain is going to be also 1%. And therefore, this is going to be equal to the same strain P divided the bulk modulus of the solid. Okay, so what I'm going to do now is I'm going to replace this change of porosity with this new equation, and let's do that. So alpha pks p divided by n, and this is going to be minus pks times initial porosity. Similar as before, p is everywhere. And now I just can solve for n, and the inverse of n is just going to be equal to, notice that ks is in the denominator of both of these, so it's going to be equal to, this is going to be negative, so alpha minus porosity divided by ks, and that's the value of n, which we said it was called Poroelastic modulus, or sometimes more precisely a second poromechanical modulus, sometimes simply Pore Modulus. And notice that it has the units of pressure, so Pascal, megapascal, and is n going to be a positive value or a negative value? N is a modulus. And because it is a modulus, it has to be a positive value. The Pore Modulus is this thing. It's kind of, you know, difficult to describe it conceptually, but it tells you when you have a change of porosity in a porous solid, it tells you how much contribution you have out of a change of pore pressure. So your porosity is going to change because of deformations of the entire porous solid, but it's also going to change because of change of pore pressure. And the contribution of that depends on the Pore Modulus, N. And we found out that if we have a system with all porosity connected, this is the value of the Pore Modulus, where Ks is again the modulus of the solid part. And because it is a modulus, it has to be larger than 0. And because this one is going to be larger than 0, notice from this equation that always your Biot coefficient has to be larger than your porosity. So if you see a Biot coefficient out there which is smaller than porosity, it's wrong. Doesn't make sense. Sometimes when you get, again, for tight rocks to very low Biot moduli, it could be 0.2, 0.3, but it's always going to be larger than the porosity. The same way, when you have a very porous solid, like for example the bone, with a porosity of 0.7, your Biot coefficient cannot be 0.6. It has to be larger than the initial porosity. Okay, so let me add just one more thing over here just to close this discussion about the Biot coefficient. We just found out that the Biot coefficient has to be larger than the porosity, and from what we saw before, it has to be less than 1. So these are the limits of the possible values of the Biot coefficient. Okay. Yes, Jack. Pascal. These are the units. This means the unit of n is a Pascal. No, it has units of Pascal or pressure. That's why Ks. But notice that it is an inverse.
So the coefficient.
Biot coefficient has no units. Porosity has no units.
Okay.
So from here we see that the module has to be the same. Cameron, you had a question before that.
Yeah, I was just going to ask, so you can get a Pore Modulus of 0?
No, you cannot get a Pore Modulus of 0 because your Ks is not going to be 0, your alpha is not going to be.
Not Ks, but he's asking if your alpha is equal to your porosity, given that.
If your alpha is equal to your porosity, that would mean that you have an n of infinity.
You have a what? Oh, okay.
N of infinity. Notice that there is an inverse there. Okay. So, if you want to write it more clearly, this is 1 over n. Same thing, okay, but just written differently. Yeah, Chuck.
It's more like a conceptual question.
Yes.
You are now assuming all pores are connected.
Yes.
Right? So if you have a closed pore that is not effective.
We're going there. Okay. So these equations help you to understand conceptually what is alpha, what is n, but are very limited because they are just considering a all connected porosity. Okay, but they are helpful in order to understand what they are. In general, we are not going to have rocks with all connected porosity. We're going to never have that. So we cannot use those equations in a straightforward manner. So we're going to have to use some other methods in order to measure the Biot coefficient. And we're going to see three methods. All right, let me tell you that still many people don't know very well what this Biot coefficient is. And there is a lot of literature out there that are calculating incorrectly the Biot coefficient. Many times just doing a simplification of all connected porosity. But that's not right. It gets close, but it's not right. So the first method, in order to measure the Biot coefficient, is that we simply use what we just used before. And we measure K with a jacketed experiment in a triaxial cell, and from this one we measure the bulk modulus. Basically what you do is you get your rock and you apply pressure and you measure strains in all directions, radial, axial, or if it's a cube, in 3 different directions. You calculate the volumetric strains, or you calculate the linear strains, you adapt them, you get volumetric strain, change your pressure divided by volumetric strains, gives you K. That's a good measurement, okay? However, how do you measure Ks? And that's where the problem comes. And you will do this, if you want to do it just a simplification, you will use Ks as K of the mineral. For example, if you have 100% quartz, you may say just get the K of quartz. And you can find that. You can find that in the literature. That's a value that it's very well known. If I remember correctly, it's 38 or 36 gigapascals. Let me write here 36. Or if you have a rock which is, say, 30% dolomite and 70% calcite, then you just do a volume average and you get your K as a function of the bulk moduli of the mineral phases. However, this is going to be again wrong if we have some occluded porosity. If we have occluded porosity, occluded is double C, right? I always get confused with this. Okay. If you have occluded porosity, that means that the fluid cannot get into all the pores. And if seen as a black box, that would mean that you may have some pores that are a lot more compliant than the mineral itself, because it's a void. Or let's say you may have a gas, or you may have a fluid, but it's a lot more compressible than having it filled with a solid. So if you have occluded porosity, then you're going to be assigning a lot lower Biot coefficient to that rock, because you are disregarding that the rock is actually a lot more compliant than what you think. So, for example, for unconsolidated sands, you can do this approximation and it's good, because you don't have occluded porosity, or it's very, very minor. But if you want to do this for a carbonate, then this not going to be that accurate. You want to do this for a shale, also it's not going to be accurate. Or for a sandstone with very high porosity, also not going to be accurate. If you have fluid inclusions, also this is not going to work. All right, that's why we have some other methods. The second method that we can do is we still use this equation, but we relax one condition. And that condition is going to be that we're not going to assume what is the value of Ks. We are rather going to measure it. And we're going to measure it, and we're going to call this bulk modulus and unjacketed bulk modulus. And basically what you do is what we did in our unjacketed test before. Subject the pressure, subject the rock to increase of pore pressure. But now, if I have occluded porosity, that's fine. Because what I'm going to measure is the change of volumetric strain. And I'm not going to assume anything about if there is occluded porosity or not. I'm just going to measure the change of volumetric strain and the change of pressure with the fluid. So the change of pressure divided the change of volumetric strain, which is measured, that's going to give me the unjacketed modulus. For example, if I had a rock with 100% occluded porosity, by increasing the pressure, I will be able to measure the bulk modulus of that rock, but it's going to be a lot more compliant than if I didn't have any pores. But let's say if I have 30% occluded porosity, then it's going to be somewhere in between. But I can measure this. I can put the rock in a pressure vessel and measure how much it shrinks, the same as the foam cup that I showed you. I can do that with a rock. However, there are some problems with this. First of all is, what do you do to apply that pressure? What fluid do you use? So the simple answer could be, we're going to use water. But that's a problem. It's a problem because what happens when, let's say we use fresh water. What happens when you expose a shale to fresh water? It can swell. Clays don't like fresh water. They will hydrate and they will swell. So this is not good. And for any clay sensitive rock, this is not a good idea. What about we don't have any problems with clay sensitivity, or let's say we have problems with clay sensitivity, but then we use a very saline solution and we use that. Do you foresee any problem with that? Remember that to measure these strains, usually we use electrical devices, strain gauges, displacement transducers, our cables inside. So if you have a brine, which is an electrolyte, and you expose that to some circuits, you're gonna have a short circuit. So in terms of experimental procedures, that's not good either. All right, so we're not going to use water because you're going to break your cell. Typical triaxial cell, you cannot use water in there. All right, so let's use gas. This could be okay if you have small samples. For example, I did quite a little bit of research looking at the strains caused by increases of CO2 pressure and methane pressure of organic rocks, because sometimes they shrink, they swell when you expose them to a gas. And usually you can do that if you have more or less small pore volumes. But you cannot do this in a big triaxial cell because of safety reasons. Generally, it's not a good idea to run experiments with large volumes of pressurized gas because it's basically it's a bomb, right? You don't want that to explode. It stores a lot of energy.
Like 1 inch by 2 inch pores, that's too big.
No, that's okay. But the problem is, I mean, if you do this in this volume, is fine. The pore volume of this is going to be fine. The problem is that you need to fill all of this with gas. And this one is relatively small, it's okay. But for example, in the triaxial vessel that I have downstairs, the entire vessel volume, it must be probably like 3 gallons. So you don't want to fill that up with gas. Or you could if you control it very well, but preferably not. Small volume is okay. Large volumes, not okay. It's dangerous, okay? Let's put it here, not desirable for large volumes. All right, so if we don't use water, we don't use gas, what else could we use? We could use oil, but there is also a problem with oil. And the problem is that the viscosity. If we are doing this unjacketed test in which we want all the fluids to get in every single pore of the rock, if the permeability of the rock is too low, then for oil it's going to take a very long time for that pressure to equilibrate everywhere inside the porous system. So you could use some other fluid, a non-aqueous fluid, which is, it doesn't, it's not electrically conductive. You could do that, but most times this is not done. Because, and why not? Because there is a third method. And this is the one that I want you to learn how to use. And from all these 3 methods, this one will be the preferred one, and the one that will give you the value, the most accurate value of alpha, if done correctly, and also will give you the value of K. That so far we assume that we have done it, but I didn't show you exactly how to do that. All right, so let's do like a little break in the sense of just going out of this page. Remember I told you that the project for the free FEM is due on Friday. If you're done with that, you can start doing the next one, which is already uploaded, and it's about Poroelasticity. And in this one, there are 2 parts. The first one is about measuring the Beot coefficient from a test which utilizes this third method that we're going to use, and basically consists on alternating cycles of confining pressure and pore pressure and measuring volumetric strain simultaneously. So we're going to see now that using the theory of Poroelasticity, we're going to be able to measure the Beot coefficient out of this data. So that's the first part. And the second part is going to be something that we're going to see on Wednesday, is more on the side of the application of Poroelasticity. And it's going to be how to predict the change of effective and total stresses when you are depleting a reservoir. So a process of depletion of the reservoir is a process in which you lower the pore pressure and your overburden stays constant. But it's a linked mechanical and pore pressure action. So we're going to need for that the theory of poroelasticity. What happened here? Okay, so let's go with the first one. You will see it's not too complicated. Is this working? No. Okay. Yeah, let me get it back. No, come on. Well, let me start this over. Oh no, I lost it. Switched off. I didn't switch off. Huh? Okay, I should not have done that break. Okay. All right, there we go. So, for the third method, then, we're going to use the first equation of poroelasticity. And this one tells us that total stress is equal to bulk modulus of the entire porous solid, just K, the same as the other ones, times volumetric strain minus alpha times the pore pressure. All right. From here, what we're going to do is we're going to solve for K epsilon. And K epsilon is going to be total stress plus alpha times pore pressure. Remember that compression here is negative, okay? So that means that this is going to be negative, and I'm adding a pore pressure times alpha, which is going to be positive. That's going to give me a negative value here. And if this is a total stress, and this is a pore pressure, what is this? Total stress minus pore. It's an effective stress, but not only that, this is Beot's effective stress, because it is corrected for the Beot coefficient. The one that we saw before without the Beot coefficient is called Terzaghi's effective stress. This one is Beot effective stress. And what this equation is telling you is that the deformation of the porous solid doesn't depend solely on total stress, and it doesn't depend just on pore pressure. It depends on both of them, and that's a Beot effective stress. So there is a unique relationship between strain and stress through the bulk modulus, but only when you have Beot effective stress. Okay. So let's see how we use this now to measure the Beot coefficient. In this method, what we're going to do is we're going to alternate confining pressure and pore pressure as a function of time. So usually when you start an experiment, well, not usually, all the time, first you increase the pore pressure, and let me do it with another color because it's not appearing very well here in the, well, it's not, that one is not appearing either, but hopefully it will improve now. First, you increase the pore pressure, the confining pressure, and after you increase the confining pressure, and only after, you can increase the pore pressure. You don't have to increase the pore pressure over the confining pressure, because otherwise your fluids are going to escape out of the rock. So always confining pressure has to be higher than pore pressure. And then you add the confining pressure again, and then the pore pressure again, confining pressure, pore pressure, confining pressure, pore pressure. Usually when I do this, I do like 4 cycles more or less. And then you can go all the way back, right? So this is with time, and also you can go back. But you will do these alternating cycles of pore pressure and confining pressure. All right. Notice that in this kind of test, which is a jacketed test, and in which also you have a confining pressure. This is the membrane. I'm going to take a little bit later about the triaxial cell, but basically you can control the, let me do this, the confining pressure outside, and if you don't have any axial stress, directly your axial stress is also the confining pressure, because it's the same applied in all directions. And inside here, you can change your pore pressure. I'm not drawing here the tubing necessary to get into the rock. I'm going to draw it later, but you can control your pore pressure inside. So if you do this type of test, then you can plot volumetric strain, and you can plot here PC minus PP, where notice that PC in this case is the same as the total stress, the outside stress. So PC minus PP, that's going to be the non-corrected effective stress, or just Terzaghi effective stress. And when you do that, you're going to get something similar to this. Okay? So let me, before I lose the connection here, let me come back. You get something like this. And it is not a unique relationship. Why? Because the equation that we saw before, it tells you that you just have a unique relationship when you correct effective stress for the Beot coefficient. So your job is going to be to find which is the parameter alpha for which, if you were to plot PC minus alpha PP, which now is the Beot effective stress, all this data, all those cycles are just going to collapse into one line. And now, here, the slope of this line is going to be the bulk modulus K of the entire porous solid, and the value that makes that possible, the alpha that makes that possible, is going to be the Beot coefficient. So there are a few ways of doing this. Either you can change alpha manually, so that you will see how the data, as you starting with 1 and lower it, and you will see how it collapses into one line. or you could solve for alpha here and do a linear regression, or you can do you can use solver and look for the alpha that minimizes an error. So just feel free to do whatever you want, but I like changing it manually. Just change the value, see how strain changes as a function of effective stress, and the value for which there is less change and all points collapse in a line. That's the value of alpha, because that's the one that shows the true relationship between volumetric strain and Biot effective stress. And that's what you have to do for the project, the first part. You will see the second part is super easy. So this is not going to take a lot of time. Probably it will just take you more time. Just go to the computer laboratory, because you're going to have to do that, and set up the model in this reservoir simulator called CMG. But also that it's not going to be as painful as the free FEM. I can guarantee. Okay. All right. So let me just close for today with just a few concepts. We'll talk about the drain problem on Wednesday, and I just want to summarize what I just said. Yes, Jack, go ahead.
So in number 2, like in method 2,
Yeah.
is there a difference when you use a gas and water beside, like when you use that medium as a pressure, is that with the rock have different responses to gas or water?
Yes.
Like how can you explain to us conceptually, like what the different response would be from the rock to a gaseous phase and a liquid phase?
So there are many rocks that have clays in them.
Okay.
And when you expose them to clay, the clay inside the rock swells and alters the microstructure of the rock. Sometimes it can break the rock. So especially if you expose a shale to fresh water, that's not going to be good, because that's going to swell the clays and probably break the rock. You have some other rocks, like for example carbonates, that if you expose them to fresh water, some of the carbonate is also going to dissolve in order to equilibrate into the pore water. So that's going to also alter the microstructure of the rock. So by injecting a fluid with water, many times you're going to be altering the rock.
Is there a consideration that the gas can enter smaller pores than water because there are capillary pressures between the rock and water?
Yes, that also can be true for pores with nanoporous pores. Even sometimes for the same rock, it may not be the same to do a test with nitrogen, with methane, or with carbon dioxide. All of those are going to have different affinities with the solid part of the rock, and as you say, sometimes they may get into pores in which other molecules they don't get. So it has to do also with the structure of the molecule and the size of the molecule. All right, so okay, so I was here. Then we said that if we calculate effective stress simply by subtracting pore pressure to total stress, that's what is called Terzaghi's effective stress. What? No, it's a Hungarian name. Yes. Yeah, this guy is from Hungary, and then he went to work in Austria, and then after Austria, he came to the U.S. Very famous guy in the area of rock and soil mechanics. And the second one is the bioeffective stress. So what does that last name sound to you? From where?
French?
Belgium. So very close. Yeah, very close. So this guy was from Belgium and then came to work to the US for Shell. So he developed all this theory close to here in Houston, and especially for petroleum engineering problems, but now it's applied in a lot of other fields. All right, so then we have Terzaghi effective stress, and we have Biot effective stress. Many people just use this equation to refer to poroelasticity. Elasticity is a lot more than that. This is just effective stress corrected by Biot coefficient, but that's not poroelasticity. Poroelasticity is a lot more. Poroelasticity includes that, but also it's going to tell you what changes of porosity you have when you have a loading of stress and a loading of fluid pressure. Poroelasticity is going to tell you what is, for example, the bulk modulus in presence of a fluid, when you have a fluid inside, something that we're going to call later on Ku, which is called undrained bulk modulus. And that means that you do not let the fluid come out from the pore space. And let me write that again. So the U here comes from undrained loading. For example, let's imagine a rock that we load under undrained conditions. We don't let the fluid escape as you apply a contraction to the rock, to the entire rock. What will happen to the pore pressure? It's going to increase, right? So with undrained loading, you're going to expect a change of pore pressure just due to the contraction of the rock. In order to predict that, also you need poroelasticity. If you are a geophysicist, you're going to be very interested in using poroelasticity for something which is called squared flow, and basically means that when you compress a rock, and if you have a fluid inside, the fluid is going to try to get out of the rock. And how much it gets out of the rock, or how hard it is for the fluid to get out, that's going to cause attenuation on wave velocities. So this square flow is going to depend on changes of volumetric strain, and among other things leads to attenuation of elastic wave velocities or elastic waves, and also leads to dispersion of elastic wave velocity. So don't worry about this. We'll talk about that later on. So dispersion basically means that the velocity is a function of a frequency. So there are going to be many problems for which we utilize poroelasticity. And we can basically, or we can simplify these to two kind of problems, which are going to be the end members of the actual solution of a poroelastic problem. And those are going to be a drain problem, which is a problem in which we assume that all the pore pressure equilibrates with the loading, and undrained, in which we assume that the fluid cannot escape as we apply a loading to a porous solid. And we're going to see solutions for the drain problem and for the undrained problem. Most reservoir simulators and simplified models, they do everything drained. They don't do the undrained part. But we're going to first talk about the drain problem and then later about the undrained. For example, if you have a hydraulic fracture propagating through a medium, and if the medium is very tight, as many shales, when you apply a strain next to the hydraulic fracture, the fluid may not have the time to escape out of the pore right away. That's going to depend on permeability, and it's going to depend on a lot of things. And how long time it takes in order to get there, that's something that we're going to see. We don't know that a priori. And if we want to look for the actual solution of that problem, we'll have to use something in between these, the end-member solutions, in between undrained and drained, and that's going to be the diffusivity equation, including Poroelasticity. And basically, this one is going to tell us what are the strains and pore pressure as a function of time when we apply a certain external loading. So, but before we go through the drain part, and then we'll talk about the undrained part. All right? Questions? No? Yes?
So the diffusivity equation, including photoelasticity, that is, again, just strain and elasticity as a function of time?
Basically, yes. And there is a diffusivity equation that does not include that,
Okay.
which is this equation. That would be without poroelasticity. Basically, we want to predict changes of pressure as a function of time in a domain, which would be a two-dimensional, three-dimensional domain, depending on permeability, viscosity, and the compressibility of the medium. Well, to add to that, we'll add the component of poroelasticity that is going to tell us the variation of volumetric strain with time.
Okay.
All right. Okay, guys. I'll see you on Wednesday. And next Wednesday, we have the exam. Right? No, Friday. Friday.
So we have class
Um,
all next week.
yes. So, well, let me see. Let me see how we get to that date. Probably, I think if I see that we cover everything we need for the exam, probably we don't have class on Wednesday. And would you prefer to have the exam on Wednesday? If we no?
Oh, I would. I don't know.
Well, I see some people no, but okay, let's keep it Friday then. Friday. But if I see that we get on time with all the materials for Friday, then probably we don't meet formally here on Wednesday, and I will just have some office hours.
So the exam will include all topics up until Monday?
That's the idea.
Okay.
Yeah. Okay. Jack, you have a question?
Yeah, can we do like not a review, but like talk about the exam?
Yes.